Oh, okay. Let's start. I see only hardcore people left, so I feel like I'll be preaching to the choir, but no, I'll stick with the original plan nonetheless. So maybe I wanna, before I actually turn to math, I wanna say a word of thanks to people who came from far away, and I hope you had a good time here in Greater Skoltech and in Moscow. Yeah. So, and I hope you'll be looking forward to coming back next year or some other year, and also spread the word that this is an okay place to visit and has a pretty nice swimming pool. And come next year, come next year, maybe even better board. So. Blackboard. So so anyway, so today we need to talk about. So the plan is to talk about this R matrix some more, and this Q character, maybe QQ character. So first, what was the R matrix? Maybe I'll remind you. So this is the so we had an algebra X was symplectic. And there was an action of A. So A was sitting in the automorphisms of X, preserving the symplectic form. And so then we had this picture where this is kind of like the Lie algebra. This is the Lie algebra of A. This is, and then in that Lie algebra, we have an arrangement of hyperplanes. Need not be, so maybe this doesn't need to be anything like Young-Baxter, so maybe I'll draw more. Something like that. These are what? These are the hyperplanes. These hyperplanes are where the hyperplanes are where the weights of, well, their equations are the weights of the A action in the normal bundle to the fixed locus. So when I have an element, and I have an element xi, which is then this, if I have a generic psi, its fixed points, this will be a vector field. That vector field vanishes only at the fixed locus, and if it sits in one hyperplane, then pick up more fixed points. Right, so here, therefore, I have this crustification where I have if I look over every point xi, I can imagine its fixed locus sitting. And then, so there will be, so at over generic points, it's the fixed locus. So here's xa, and here's x itself. And what we would like in this diagram is we would like to have, for every cell of this arrangement, we'd like to have a map to every cell in the boundary. So like we'd like to have maps from, we kind of want to xa, the whole fixed locus. We want to have, I write a correspondence. So this means we have a correspondence between these two. And that also disagrees with the fact that if I take any subtors, then this correspondence is composed in the way we want, where A prime is a subtorus in A. This x itself being corresponding to the trivial subtorus. And what this correspondences should be, this this is a correspondence. A prime is any, so this A prime, so you should think of these are different every cell in this arrangement corresponds to a subtorus. Yeah, it's like it's something here, yeah. A prime inside A, that is true. Thank you. Okay. So, Yeah, this will be some this will be exactly the same correspondence for elliptic. The other right, but that's because we're doing so this A, this is a sub group here. And everything we're going to do, so we want to, so there's some bigger torus here. And we would like, there's a weight of this torus, kind of h bar is the weight of symplectic form. So when we do everything, we want to do everything T equivalently. And so therefore, in particular, all these numbers, all the weights we'll see, there's also h bars there, and those are the shifts. So this is what like the correspondence, which is an improved version. So improved version of the attracting manifold. So it means, so again we had this picture yesterday. We have all of X, and we'll have the fixed locus. And then we have a correspondence, which is, we look at the attracting manifold. So this is the attracting, which is the set, you can think the set of all, it's a pair, a point X and a fixed point F, such that if I take the action of like, what would I want to do? I want to do A times X as A goes to 0 equals F, where A is, in that picture, is the exponential. Right. So every vector here, every rational vector here corresponds to one parameter subgroup, but that, that doesn't, for that, it doesn't have to be an actual one parameter subgroup in a virtual one parameter subgroup. And we discussed that this you can't really use this as a correspondence because, well, what's going to happen is that this is not like this attracting manifold. If you follow it, it's going to hit some other fixed point, and so that will be. These are like the simplest examples of this are when X is a T star of Grassmannian. And these guys are the attracting manifold of a torus action inside Grassmannian. These are Schubert cells, and these are the in the cotangent bundle will be conormal to the Schubert cells, and the already conormals to Schubert cells. Their closure are complicated. We don't want to use that. And the idea yesterday was, well, one idea yesterday was, well, maybe you first perturb the action a little bit. So if I perturb it, this trajectory is going to go, somehow like that, because in the perturbed world there will be no. A retracting trajectory to one fixed point will not hit any other fixed point because the perturbed varieties are affine and there are no curves in affine variety. And so then you take the limit, and then we find that, well, you should add you should have added to this attracting manifold, you should have added some multiple of some attracting manifold downstairs. Okay, so that's the idea, and I think Michael, I think, did the computation for T star P1, which I'm not going to redo it, but I will half assume. So was that not a success, or?
It would be successful to size.
Okay. What?
He chose like for step plus and for step minus the opposite polarization.
Oh, that's a bad idea.
You just look at the matrices he writes and you see that they have just
Yeah. Okay.
But that should give you a common
So. So maybe we'll review some of the ideas there. And so again, so maybe I'll just copy the same picture. Copy the same picture we'll have. So we had maybe one component of the fixed locus and another component of the fixed locus. You should imagine these are not points, these are some varieties of some dimension. And so then we have attracting manifold. And then at closure, hit some other component. You know, you imagine that it's not ends here. It's some subvariety that contains the closure contains some other component. And the idea is that we should add some multiple to the attracting manifold of this lower component. Right? Whatever is we took the closure of this one, and this is not the right thing to do, right? Which is and the way to know it's not the right thing to do, you can try with, you can see that triangle will fail for even like P2. That triangle diagram that this triangle of the fixed, this triangle lemma, and this is triangle lemma what gives you Young-Baxter. So the Young-Baxter comes from this triangle. And that will fail already for P2 if you just take the closures. And so then, so we would like to add some multiple of this. So maybe which multiple should we add? And so then the idea is to consider. So we'd like so maybe there is a point P1 and point P2, and we would want to construct. So the name for that was the stable envelope, and the origin of that was because the attracting manifold, another name for it is the stable manifold, and envelope means not just the stable manifold, but also something you need to wrap it into. You need to add more stuff to it. Kind of. So they would like the stable envelope of this now P1 to start with like attraction manifold of this P1 plus some multiple maybe plus something tag plus something times the. Well, let's just, for the sake of the argument, let's suppose these are just points. So then maybe this will be then there's just a multiple of the attracting manifold. So this closure of that plus some multiple of attracting manifold of P2 plus some stuff. And so what would be, how do we determine this multiple? So again, the picture is that we perturb this action. The trajectory for the perturbed action goes not very gracefully done. So the trajectory for the perturbed action that goes something like this. And so if we remove the perturbation, we'll wrap some number of times this attracting manifold, and we'd like to know what that multiple is. Now, there is, for geometries like T star P1, there's a cheap answer to that, and the cheap answer to that is that we had this X. This was after also when we had this moment map, and that was exactly fiber over 0. And this we can deform. We can put in a family. We can put in a family where you take T times the identity matrix. You know the identity matrix like this. And this will be, so this will be deformation xt. That's the fiber of that. And that is a deformation that makes, you can, so in order for Nakajima right, you can write this deformation explicitly by just choosing different value of the moment map, different level of the moment map. So this deformation, so moment map, that's written something, this written in terms of symplectic form. There's a symplectic form comes in the definition of this moment map. And so this moment map is preserved. This torus A acts on fibers of this diagram, acts on fiber-wise. But the bigger torus, and the whole idea is we need to work agreement with the bigger torus. Otherwise, we're going to get something stupid. It's like there's deformation parameter, namely the weight of the symplectic form. That's the weight of this bigger torus. This bigger torus, the scale symplectic form, and in particular symplectic form will scale the moment map. The bigger torus acts also on the base. Of this deformation. Right? And so that so there's in fact it acts more or less with the character more or less h bar, or h bar plus minus 1, I can't remember. Okay. So that's that clear? So then I say, well, we're trying to compute something in T-covariant cohomology or T-covariant K-theory. Let's do cohomology first. Cohomology easier. So then the condition should be that if I restrict stop P1 to the point P2, if I compute the restriction of this manifold here, I know that if I turn off this weight, then I have an equivariant deformation that makes this manifold miss the point. So this is, in other words, this is 0 mod h bar. Here, and so if in cohomology, if we're looking for an integer, and the condition is something vanishes mod h bar, there's the coefficient. We get one shot, and this is the right thing to consider. Did you guys do this computation yesterday? So what was the computation for P1? For P1, so this is maybe my picture of T star P1. So this is T star P1, and maybe let's imagine this is 0, this is infinity, and let's say this is my weight A. A takes this point and attracts it. So A goes to 0. A takes this point, attracts it to 0. So the attracting manifold is actually P1 itself. And then if this weight is A, then this weight is A in, or maybe I'll write. So if I know cohomology, I want the additive notation. So maybe maybe I'll take A to be exponential of what? I guess it was psi. So we put psi here, minus psi there. And then this is the cotangent direction, so this is minus psi minus h bar, because that's the, and I will use h bar both additively and multiplicatively. Okay, this is annoying, but otherwise it's just too complicated. In K theory, in homology it's additive, in K theory it's multiplicative, and then because the way the symplectic form, well, this, anyway, this is how it works. So this minus psi, this will be psi plus h bar, right? Minus h bar. So now if we compute we compute this, maybe denote multiple m, then the attracting manifold of P1, the closure of that is just of P0, that's this P1 itself. So that would be, in my computation here, that would be psi minus h bar, right? Okay, and then plus this multiple, which is now the restriction of a manifold to a point is the product of all normal weights. So here the restriction of this guy is psi minus h bar, because that's the normal weight here, and here the normal weight is minus psi, so it's minus psi. And we see that this equation has a unique solution when m equals 1. Okay. Yeah, question? Yeah. Not the intersection, it's just the perturbation is going to go to this cycle some number of times. I mean, so it's not, you can, right? But that's actually, this type of argument is not going to work in K theory, because in K theory, so how would like to define in K theory? In K theory, h is a multiplicative variable that its vanishing means mod minus h1. But in K theory, there's like a million things I can put here to put. In K theory, I can put any sheaf, right? I can put anything. I mean, just like a million things I can put there. And so the right thing to do is not this, but something else. So maybe I'll put it back here. Is that in homology, this is a Lagrangian. This is Lagrangian. So in particular, the restriction to a fixed point, this would be, in particular, half dimension. Dimension equals 1/2 of dimension. Well, let's I assume that for the sake of argument, I assume that dimension. In general, it's a Lagrangian. In general, it's a Lagrangian in the product of x and the fixed locus. So its dimension is 1/2. Is the average of the dimension of this and that, but it's but let's, for the sake of the argument, assume this. So this means that the restriction of this to a point has to be a polynomial. So what we know, it's a polynomial. It's a polynomial in A and H of degree equals 1/2 dimension x. Or sorry, not A, psi. Okay. And so then the fact that it's in fact divisible by h, we can rephrase as saying that in fact the degree in A is really less than 1/2 of the dimension x. That's so in xi again. I apologize. I use xi here. We can do the same computation again. I can see that of course there's one and only choice for this. It's not going to be a different computation. It's going to say here's xi minus h bar plus some multiple of minus xi, and we need, instead of killing things mod h, we need to kill the top degree in xi. Okay, there's again same conclusion, m equals 1. But that's much better, because this, in K-theory, the condition that some polynomial is of some bounded degree, that's a condition we can just really formulate. I mean, it's just really sensible condition to make it in K-theory. So what would be, how do we say it? So this is, how do we say it in K-theory? So then we'd like to, so now in K-theory, we'll put the weights the way they should be. So this is the A, and this is 1 over A h bar. Here's 1 over A, and here is A over h bar. And so, okay. And so, what is the restriction if I take the structure sheaf of the same, so I have this manifold here. And I take the structure sheaf of this actual, again, the support of the stable envelope. And I restrict it to the point to infinity. Well, what's it going to be? This is defined by one equation. Here it's defined by one equation, which is the product of these two coordinates. Right? So the normal weight to this manifold. So this, you see, this is defined by kind of x, y equals 0, where this is the weight of x is 1 over a, and the vector y is a over h bar. And so then if I multiply, this has weight. This equation is in the coordinate has weight. The normal weight is 1 over h bar. Means this restriction is 1 minus h bar. Guess you have to invert the weight. And we see it satisfies, well, it satisfies both conditions. It satisfies the condition that is 0 when h bar is 1, but this is the condition not going to define it uniquely. But it is also the condition that its degree in A is in fact 0. What's the degree? So this is a priori. A priori, this is a priori a Laurent polynomial in A and h bar. When we compute the degree of Laurent polynomial, the degree of Laurent polynomial, what should it be? It's not a number, if you will, like the degree of a polynomial, round polynomial, should be roughly like how many zeros does it have in the torus, in the corresponding torus. Has something to do with something like that. And so this the Lagrange polynomial is really its Newton Lagrange polynomial, maybe call it P. It's really the Newton polygon. Newton polygon of P. In fact, Newton polygon up to translation. And so then the condition is that if I so the right condition and the right axiom that if I take the Newton polygon of this stable envelope of one point and restrict it to the other point, that should be smaller than some, so this condition at some degree is smaller. That means this really, this Newton polygon sits inside some other Newton polygon. This should be sitting inside the Newton polygon on something canonical half-dimensional. Maybe you can take, so this is well, you can take it to be, say, polarization at this point, which is it. So this is some canonical something. Maybe I'll like let you take the. I'll do cheating. I will not tell you. So you need some canonical choice of a Newton polygon of taking half dimension, something of half dimension. And so this canonical choice goes into how you normalize the stable envelope of this point restricted to itself. In variables A. In variables A.
So before when you wrote the structure sheet restricted to infinity equals 1 minus h bar, you really meant the stable envelope of the structure, the K-theoretic stable envelope?
Well, I took the structure sheaf of that submanifold.
Is that, the structure sheet of the perturbed submanifold?
Of the union of actual, so if the actual stable envelope is some subvariety, the cohomological one, some actual cycle, and I took the structure sheet of the cohomological stable. Yeah, exactly, yeah.
So that's not the same thing.
No, it's not the same answer in general. I just gave you what the answer should look like. It's an example. So this is.
It did turn out to be the same in this case as the K-theoretic stable envelope.
Right, but in general, something contains much more information. So this says that this says that this is there's oh no. I'm nowhere near the Q characters and QQ characters. Yeah, right. So this is maybe we'll somehow I'll give you the highlight. So how you normalize this? Yeah. Right, but this somehow, but this is right. This we can talk about this next year. So this we have to get the Q. We have to get the Q characters, right? So the point is that there's a how you normalize the stable envelope at itself. You think, well, maybe I'll just take it, just the structure sheaf of attracting manifold, but that's not the best choice. You have to twist it a little bit to agree with polarization. You had the structure sheaf, so the condition is that stable envelope of P1 of some point P1 is not really attracting manifold of P1. It's just some line bundle here. You have to put this line bundle, or you're going to get in trouble like Michael did yesterday. And so this like bundle has to do with polarization. So then maybe we'll skip that business. So okay, and so then this is a fine condition, except there's this up to translation business. So in principle, what I can is I can put this into not put for condition not that this polytope is included in this polytope, that this polytope is included in some shift of this polytope. And that's a really useful condition to put. So you can put some shift which will be somehow canonically determined by these 2 points P1 and P2. We need some. So this sits, where does this sit? This Newton polygon sits in the weight lattice of A. And so we need to shift, we want to shift this polytopes relatively by some weight of A, or maybe if I want to take a if I really want to take a polytope, then maybe we take this weight lattice and tensor it with R. So this is, when you take a polytope, it will be like really polytope, or really something solid. So we would like to shift one with respect to another. We need some weight that canonically depends on the pair of points. And the way to do it is you choose an arbitrary line bundle L. It's in peak, a covariant peak A of X. Doesn't matter. Tensor R. It's like it's a kind of a rational. People call it the rational line bundle, or in this case R line bundle. And you shift it by the weight. Put the weight of L at the point P2 minus the weight of L at the point P1. So you get not one choice of this stable envelope. In fact, you get a choice indexed by some arrangement here. So L, so this is my peak X tensor R. And there's some hyperplanes which are now they periodic with respect to, so if there's an action of peak itself here. Peak is the set of line bundles. Maybe it's too late for this. So there's some arrangement, something like that. Some periodic arrangement of hyperplanes. And you get what?
How do you define this?
It's a separate issue, which is next year, as Igor points out. Yeah. So then, in fact, it depends on a point in an arrangement, on a choice of a facet. So this is some integral polytope, and there's some other integral polytope. And if you have an inclusion of integral polytopes, if you move it a little bit, the inclusion will stay. In the state, we have one integral polytope included in some shift of another integral polytope. So if you move that shift a little bit, this will be still included. Right? So this stuff is kind of locally constant in L, and sometimes jump. And so then you get in fact not one coproduct, but a family of coproducts indexed by the facets of this arrangement. This stuff gives me an R matrix, so this R matrix will depend on the choice of this line bundle called slope. And so it's not one coproduct, but a bunch of coproducts, which is well known in in ordinary quantum groups, that then it has not one but many coproducts. And in fact, Pasha discussed two. Pasha discussed like the normal one and what people call the Drinfeld coproduct. It's kind of the at infinity. So in this picture, there's somewhere like the coproduct that Pasha discussed, and then there's at infinity the coproduct that the Drinfeld coproduct. And this Kharoshkin-Tolstoy factorization of R matrix that was very important in Pasha lecture. There was some factorization of R matrix. Where does factorization come from? That if I choose some path from minus infinity to plus infinity, this is the analog for in the classical if I want to construct the loop group of a finite dimensional if we want to construct the quantum loops into a finite dimensional Lie algebra, this arrangement is just the corresponding affine Weyl group arrangement, and a choice of roots. So these are just all roots of the affine Lie algebra, and the choice of path from minus infinity to infinity is the choice of a normal ordering of these roots. And so what you want to do is you want to factor. So you can factor the R matrix, or rather not factor. You can if you want to compute the R matrix here, so R matrix at this point is R matrix, R kind of L, which is stub L and then kind of unstub L inverse, this sort of thing. You choose the stable envelope that depends on L, and then the opposite stable envelope depends similarly on L. That's the R matrix at L. And if you want to compute it, you might as well first see how the R matrix changes if I cross the wall. If I cross the wall, it changes also by a solution of Young-Baxter equation. So if I cross the wall, there's a solution, some solution of Young-Baxter equation that you put here. There's some kind of R wall in which you don't change the attracting direction. You just take, so the R wall is just kind of stub L plus stub L minus inverse. Right? So this is something much smaller than this big guy. It detects how this stable. So this depends on the spectral parameter. This in fact does not. It depends on it in a trivial way. Because this is like the R matrix. So for every wall there is like every wall is like a root in some. Every wall is like a root in some loop algebra, and for that wall there is it's some quantum group. Corresponds. There's some R matrix there, but that quantum group is not a loop group. It's just some quantum group. So the spectral parameter here has some trivial dependence here, and so you can factor this guy into first going to infinity. At infinity, you're the situation when the stable envelopes are just, so at infinity, you should think of the stable envelope as just really being like they take the class. So maybe this is something kind of important. So the stable at infinity, you should think of them as just being, I don't know. Guess I'm searching for the right color to convey my thought. So at infinity, you should imagine that stable envelope is just lives at that point, because everything below it's shifted infinitely far away in the weight lattice. Right? All these terms are gone to infinity, so all the restriction to other fixed points are just gone. Yeah, you can do this exercise. It just really says somewhere in the weight line there's some shift by the weight, and that weight's gone to infinity. So in a suitable ring or whatever formal power series or anything, you can just imagine that the restriction at all other fixed points of this stable envelope is just really zero.
Can you explain what you said a minute ago that this R
Right. So this is, you should imagine what is this picture for, like, for this is, if I were to make this picture into the ordinary, like, you know, sorry, if I were more accurate, I could have drawn something like this. Would be also misleading because in general this is nothing of the kind. But this is the picture you're going to get for UQ of UQ UH bar. Sorry. This is the picture you're going to get for UH bar. UH bar of GL3 hat. Right? These are really the roots of the affine Lie algebra. And for every root, there is like a root subalgebra. I mean, it's if you know the theoretical quantum group, it's not really canonical defined, but if you have chosen a path which corresponds to the factorization of the longest element in the while group, then you do have for every element, for every root, you do have a subalgebra here, and at the subalgebra there's inclusion of a whole bunch of UH bar of just SL2, not affine. For every root here, you have something like that. And the corresponding R matrix here is just, in this lecture, is just the wall R matrix for the, what happens is I cross this wall. That answer your question? Okay. So this gives me a factorization. So Pasha had this. So in Pasha's lecture, we had this factorization where the R matrix R of U had this product form. There was the R, maybe I'll write R delta, because this is, I don't know why delta. For Drinfeld, I guess. So this is the one, this is the R matrix at infinite slope. At infinite slope. And then there's kind of R plus R minus. This corresponds to, and if I go here, I cross all these walls first, and I go here, and then I complete here. And this is the matrix coefficient. So this was the matrix coefficients of this guy. This were the, so this would be, if I look at the matrix coefficient of this, they would give me this generated this big commutative algebra, of which we will take in trade. Right? So to capture the representation, to capture the character of the module, you were looking for the action of some big algebra, and then tracing these operators to take the trace to get this Q character. But so like I said, that this is at infinite slope. This is something very simple. So if you look at this coefficient here, so maybe so I know I gave this discussion in K theory, but let me, in the interest of time, let me talk about this guy in cohomology. So then it's so what's it going to be? So if I have a fixed point P, then this will have the this also depends on U. at the fixed point P, I'll have some attracting direction and some repelling directions. So attracting and then repelling. And so then you should think of this as right. So actually, so let's do concrete situation we really want to do. So we have we now have x, and we have so x has maybe have a torus. U acts by some matrices of some formula 1, 1, 1, U, U, U. This acts on all the framing spaces. This is framing for x, and the fixed locus is a disjoint union of products of the Quiver variety of the same type. And then what is the, so that's an exercise we did. So then what are the attracting and repelling manifolds here? The normal bundle, so if you look at this is an exercise you should have done, normal bundle to this product is kind of x1, in terms of Quiver representation, x1 of x1 into x2 plus x1 of x2 inside x1. So when I write this, you have these are modular space of Quiver representation. These are x between this corresponding Quiver representation. And the way U acts on the fixed component just scales. It just scales the second component by U. So this will have the weight U, and this will have the weight U inverse. Those are exactly, because this is the tangent space at the product like this. The tangent space at any x is x1, and then the tangent space. This is geometrical direct sum of Quiver representation. So the tangent space there, it's going to be the tangent space here, tangent space there, and the cross terms are the x.
And it doesn't do anything to the internal.
That's right. That's right. It's only acts here, and so this guy here, that really acts. This guy here, well, in cohomology, is going to act by the ratio of the characters of these spaces. Right. These spaces are dual with the. This is the dual. These are dual with the shift by. Dual with the shift by h bar. Because the symplectic form gives you duality between these two spaces, but the symplectic form itself has the weight h bar. And so this guy will have, this will be an operator which will have the form, the kind of form is like a product over U plus W over U plus W h bar, where these are the weights. These are kind of the churn, these are the churn roots, maybe we want. These are the churn roots of this bundle here. Okay. And now when we take matrix elements of the R matrix, we fix what's going on in one of the space and look at the other. Right? When we take matrix so R matrix, the way it acts in X2 is by taking some matrix element in X1 and see what it does as an operator in the other. And that object, now if I looked at this X1, And I think fix what happens here and see how it varies as a function of x2. In x2, this is kind of linear in x2, in the corresponding representation. I apologize, maybe I should write f1. I mean, this would be, otherwise it's x is the moduli, and the actual representation is alright f1, because it's like the sheaf f2, f1. If I fix one, then it's linear in the other. So in fact, these guys generate, so the matrix, these guys generate, so this kind of x between something fixed and your variable f, so this exactly generates all characteristic classes of vi's and wi's. This is going to pick up all the algebra of operators you're going to pick up are just exactly characteristic classes in the tautological bundles.
Where is f now? Is that
x is the modulo of f. And so now I fix one sheaf, and I see it as a function of the other. This is some virtual bundle.
Where is fixed? Is the fixed one going to be anywhere? Or
Yeah, this is, I mean, it's a fixed, some arbitrary representation. So arbitrary fixed. So then this is like auxiliary space in the physical space. If we do this, then this picks out. We can pick out. This will be this is linear. This expression is linear in tautological bundle, and it picks them all. Who else is following this discussion? Raise your hand. So if I have like a Quiver variety is a moduli of some object. Moduli of, you can say, it's always moduli of Quiver representation, but you can also think about concretely like moduli, like instanton moduli space, the moduli of bundles. The moduli of some object in some abelian category. And you're given to you over this moduli space. You have a standard vector spaces vi and wi's, and then anything else which is linear in your representation, which is linear in your sheaf, you can reduce to this vi's and wi's. And so in particular, if you ask yourself what would be the x space between some fixed sheaf and some arbitrary sheaf, if you're talking about like sheaves on surfaces, which is the instanton moduli spaces, if you give yourself one sheaf and ask for x in this fixed sheaf into your variable sheaf, you can pick all tautological bundles there. In fact, you're going to pick them exactly. What you're going to pick exactly in K-theory is exactly the K-theory of that. So these operators, the one come from the matrix elements of this matrix in the middle. For Pasha, there were just whatever Drinfield's, I forgot. Drinfield loop, whatever, something commuting this loop generators. They're coming from here, but what they are geometrically, they're just operators of multiplication by an arbitrary element in the arbitrary expression in tautological classes for vi's and wi's, but packaged in a particular way. And that packaging, you see the rate. I mean, these are the expressions that Pasha writes, right? It says this eigenvalue is going to take this form, and it does, right? Okay. So then if I take the traces of objects like this, if I take the trace of this R matrix, this is going to be this Q character. My watch tells me that I've somehow moved enough. I don't know. Okay. But now what is the QQ character? And now how you should? Yeah, exactly. Now the school begins. Yeah. So QQ character is something else. What? G is right. So maybe I'll take a minute to explain what it is. So Q characters, as I was trying to say. So okay, so then maybe I'll say it one more time, because they can in Pasha's lecture there were some commuting. There will be some commuting elements of the size of if you were trying to write quantum loops into some Lie algebra. If you take quantum loops in just Cartan of this Lie algebra, you had so many commuting generators, and they were lifted to the quantum group as the matrix elements of the middle term in this factorization. And now geometrically, you identify how this guy is going to act, and you can read off that Q character from just, if you actually look in your Nakajima Quiver variety, you can read off that Q character. It's going to given to you. It's going to given to you, visibly by that. Okay, okay. Maybe it's an exercise in the kind of computation. So if you know how to compute the classes of these objects in K-theory, then one of the exercises were to compute the class of the tangent bundle in K-theory. If you know how to compute the class of the tangent bundle, then you also know, if you take the tangent bundle at a point which is a direct sum, then you also know how to compute the x's. So that I presume you already did this exercise. Anyway, Q characters are the traces over maybe the K-theory of Nakajima variety of operators that are operators, operator of classical multiplication. K-theory is a ring. Their operators as commuting operators, just multiplication there. And so this is me. If I have a K-theory class, then there's operators, i.e. operators kind of, alpha, tensor, something. It's an operator. So if I take a trace of this operator, you get the Q character. And this is, and the reason that you write them in a funny way is because you use some particular generating function for all possible operators. And now the Q character, so which is also, okay, how do I can write this geometrically? This is like I take this operator of classical multiplication. What's the trace of an operator? It's like I pair the operator of classical multiplication, this operator, with the identity operator. Everybody agrees that the trace of an operator is the same as the inner product of an operator with the matrix, which is 1, 1, 1. Somehow, everybody cool with that? So, what is this product? This product is really the integral, because these operators are after all, we think of operators in K-theory as correspondences. So it's the integral over x cross x. Of what? What's this operator? This one operator. One operator is easy. One is just the diagonal. So you take the diagonal. And the other operator, it's what's the operator of classical multiplication by some class alpha? Well, you put that alpha on the diagonal, right? Diagonal sits inside. A diagonal is a copy of x. You kind of push, you push forward alpha under the inclusion of diagonal. Okay, you put your class alpha here. Right? So now when you integrate, and what you're going to do? So that means when we integrate on the diagonal here, we have to take into account this diagonal here. So when we integrate, we might as well treat to diagonal, but there's this other diagonal here. And so that would be the integral over x of the class alpha times the times, I'll write kind of the Euler class. Euler class means alternating sum of exterior powers of the cotangent bundle to x. And because that's the norm, this is the normal bundle, this is the dual to the normal. The normal bundle to diagonal is the tangent bundle. And that's the dual, and you put the Euler class of the dual bundle. Okay? And so now the QQ character. Anytime you see something inside the Euler class by itself without any variables, you should feel, yeah, this can't be right. That makes sense? And if I have an alternating sum of, so this is what is this? This is summation over I minus 1 to the I, and then I forms on x, omega I on x. Okay. Anytime you have something like this, and there's just minus 1, you think this is not right. And you should put a new variable here, which you should think of this variable maybe called m. Well, in Nikita's world, it's called like epsilon 1. Okay. So the QQ character is the integral of alpha. You put the Euler class of T star x. Tensor M. You can, in fact, so you can write it in a million other ways. You can say that this is like a you can compute it. You can say that this is the pairing. You can write it like this, that this is really the pairing between the operator alpha tensor and, in fact, some kind of you can put here, there's some kind of vertex operator. I'll just write a vertex operator. What's that vertex operator? Is that if I take x cross x, since I'm going to restrict this to diagonal anyway, I can write something. So the point is that the tangent bundle, I remind you, the tangent bundle to x, this is like x to 1 between kind of f. But this you can write that this is the same as x to 1 between f1 and f2, restricted to the diagonal when f1 equals f2. So in fact, there's some operator you can define on the whole product. That is the Euler class. This guy here, the Euler class of m times this x1 plus 1 is 2. And the dual, that doesn't really matter. All these varieties are symplectic. You can replace the other way around. So, and that is some operator now. There's some dense matrix on the product. And this for Nakajima Quiver varieties, these are really R. This is some kind of vertex operator. For Nakajima Quiver varieties, they really are some vertex operator. You can also say that this is like I put some trace. This is one way to think about it. And then another way to think about it is that I take a trace with some operator, which is, so this is the QQ character of a tensor product is not going to be equal to the QQ character. So the QQ character of QQ character of kind of V1, or maybe not V1, some module is not equal to the QQ character of M1 times QQ character of M2. Just precisely because here I put something which is, is a bilinear. Right? Means previously we were looking for x between your sheaf and some other probe sheaf, but now here we're just really talking x1 between sheaf itself. Right? So when we try to compute the QQ character of tensor product, it will be cross terms. This has cross terms which this doesn't have. Yeah? And what are the cross terms? Cross terms so, all right, I forgot to say here, well, I forgot to say if you have say finitely many fixed points, then this of course will be the summation over the fixed points of some torus action, x whatever torus action, and you just take the alpha restricted to the fixed point. So this really would be the trace, because when you restrict the Euler class for fixed point localization, you're going to get the Euler class in the bottom and the Euler class on top, and so you really get the trace of an operator. But now this cross terms you're going to get in this formula. What are they going to be? The cross terms will be the fact. So if I have, again, we've decided that there's some weights. So maybe there's like there's x1 f1, there's x f2, and there are cross terms. There's x f1 f2 and x between f2 f1. These are the ones, right? And so if these are my if I think of this as having churn roots w, then this will have churn roots minus w minus h bar. And let me write the cross terms in cohomology. So what the cross term is going to be? It'll be like m plus w divided by w. I'll just write in localization form times minus w minus h bar divided by plus m divided by minus w minus h bar. This is the extra terms, like a product over all w, the way it's here. And so these are the extra terms I'm going to pick up in. These are here. The Q character of this is like the trace of one times another plus this guys times this guys rather. And how can I think of this? Maybe I denote this expression C of m. And what sort of equation does C of m satisfy? C of m is so if I take C of m, and let me take C of m and divide by C of m plus h bar. What I'm going to get? I'm going to get product of m plus w over m plus w h bar. And here I'm going to get minus w minus h bar plus m over minus w minus h bar. That correct? Minus m, sorry. Plus m. Sorry, I apologize. Plus m. Did I do this? This is elementary math. I hope it's correct. It's okay? And so where have we seen this expression before? This is r delta of m times the r delta divided by r delta of minus m. So in other words, your QQ character, it's not a homomorphism, but it remembers exactly this Drinfeld. I mean, the kind of stuff you need to put in to make it a homomorphism. You can say it like this: that this guy is not this expression, but it's this expression acted on by some operator. So you can say, well, you can say that this Q character of the tensor product is not just the product. It's you apply some operator to you have two functions, and you just not multiply them, you apply some operator to them. And that operator you have to apply, that's the solution of some, well, maybe another equation to nail it really completely. CO0 is 1. So these two equations, of course, nail it completely. So that's the extra operator you have to put in. The extra operator you have to put on this guys has to do with this Drinfeld's R matrix. In some, you digest it in a certain form, but that's the conclusion. Well, like Igor said, there's always another year, and so maybe we'll have to make a short break between this year and next year, and so with this in mind, maybe I'll stop here. What's the best thing about this operator for like us? I should assign this in numbers. How do you think about this operator? What's the best way to think about this?
Is this operator situated in point M?
No, it depends on M. M is like it's some field we should give the mass M. It's just a carrier. M is a carrier. It's something which comes from here. This is lots of ways that M. In some, if you engineer that stuff in some 10 dimensions of maybe M would be a point somewhere and somewhere. Usually, like it says here, just the mass of this. Equivalent variable. We have bundle. It's a shame for the bundle to go without the weight. Every bundle has to carry something. Well, here you pulled it from. Okay. Now, how about was the 10-minute break is enough? Yeah, let's make a 10-minute break. And then the school will